This is a tutorial on the mathematics of chemical reactions, which we also call stoichiometry. So stoichiometry is about the relationships between the different chemicals in a reaction. You've already learned how to convert from grams to moles to liters and to particles. And in this chapter, you're going to learn how to relate, for example, grams of one reactant with, if I use that reactant, how much product should I be able to make? It's very much like a recipe. So let's take a look at an actual recipe, and I can show you how stoichiometry is really the same thing. So let's suppose that this is our recipe for making cookies. 2 teaspoons of vanilla, 1/3 cup of oil, 2 cups of flour, 3 eggs, and a 1/2 cup of sugar. And if you mix those ingredients, you would have the amounts to make 1 dozen cookies. So the question says, what if I want to bake 8.5 dozen cookies? How many cups of oil will I need? Okay, so in a stoichiometry problem, what you'd do is you would start by writing down the piece of information that was given, which is 8.5 dozen cookies. And then we would go to our equation and we would look at the relationship between the dozens of cookies and the amount of oil. So for every 1 dozen cookies, I'm getting this from up here, I need 1/3 cup of oil. So this is my relationship between oil and dozens of cookies. Now, dozens would cancel, and I would do 8.5 times 1/3, and that would give me 2.8. So I would need 2.8 cups of oil to make my cookies. Let's look at another one. I have 8.5 teaspoons of vanilla. So I would write 8.5 teaspoons of vanilla, and they want to know how many dozen cookies I can make. So again, my relationship between teaspoons of vanilla and dozens of cookies would be, I go back up to the top, for every 2 teaspoons of vanilla, I make 1 dozen cookies. So my relationship is 2 teaspoons of vanilla make 1 dozen cookies. And again, I can now cancel my units. Teaspoons of vanilla would cancel, and to get my answer this time, I would do 8.5 divided by 2, which would be 4.25. That's how many dozen cookies I would be able to make. So this is using, obviously, a recipe, but stoichiometry is based on the exact same thing. So when we look at this chemical equation, 2 hydrochloric acids react with 1 zinc to make 1 zinc chloride and 1 hydrogen molecule. These should be subscripts. Alright, so this is the relationship. So that's telling me, I could interpret that to mean that for every 2 hydrochloric acids, they would react with 1 zinc, they would make 1 zinc chloride, and they would make 1 hydrogen molecule. Or that would also mean that 2 moles of hydrochloric acid would react with 1 mole of zinc to make 1 mole of zinc chloride and 1 mole of hydrogen gas. And you might say, well, I don't understand. How would moles be the same? Well, remember, moles is an amount. So if 2 hydrochloric acids react, then that would mean that 2 times 6.02 times 10 to the 23rd hydrochloric acids would react with 6.02 times 10 to the 23rd zincs, and they would make 6.02 times 10 to the 23rd zinc chlorides and 6.02 times 10 to the 23rd hydrogens. That's the relationship between them. So just like it would take 2 molecules of this to react with one of these, it would also take 2 moles of this to react with 1 mole of these. So let's take a look at the problem. How many moles of hydrochloric acid react with 2.3 moles of zinc? So here's how you set this up. You always start with the piece of information that you've been given, which is 2.3 moles of zinc. Now, we have zinc, and we want to know hydrochloric acid. So we put the one we want to know on the top, the one we want to cancel on the bottom, And now we look at our relationship. So for every 1 zinc, we need 2 hydrochloric acids. And now we solve it. So in this case, it would be 2.3 times 2, which gives us 4.6 moles of hydrochloric acid. Now let's look at one more. So for our second one, they're asking us how many moles of aluminum nitrate will be made when 0.75 moles of silver nitrate reacts, and they're giving you the equation. So again, our first step is to start with the one piece of information you've been given, which is 0.75 moles of silver nitrate. Now, they're giving us silver nitrate, they're asking us for aluminum nitrate. So we're going to put the one they're asking for on the top, and the one we want to get rid of on the bottom, and now we go to the equation to look at the relationship. And the relationship is that for every 3 silver nitrates that go in, 1 aluminum nitrate comes out. So in this case, to solve the problem, we would do 0.75 divided by 3, because it's on the bottom. So 0.75 divided by 3 gives me 0.25 moles of aluminum nitrate that would be produced. Okay, so now we're going to take it a step up. Now here's the thing. We cannot relate these ingredients with one another based on how much they weigh. In other words, we can't say that 1 gram of this reacts with 6 grams of this to make 6 grams of this and 6 grams of that. That doesn't work. We can't say that. Because remember, every element has a different weight. So we have to use moles because we know that they are related to one another by moles. We do know that 1 mole of that would react with 6 moles of this to make 6 moles of this one and 6 moles of this one. All right. So this time, instead of giving us moles, they're giving us grams. So if we start with 1.5 grams of glucose, C6H12O6, and they want to know how many grams of water you would make. All right, now here's the thing. We already learned that if we have moles, we know that we can relate glucose and water to one another in the equation. But the first thing we have to do here is we're going to have to change our grams of glucose to moles of glucose. So 1 mole of glucose, we would go to the periodic table, and I'll save you time. It weighs 180 grams. Again, that would come from weighing the weight on the periodic table. Okay, so if we divide that out, we get that the amount of moles of glucose we have is 8.3 times 10 to the negative 3 moles. So this is how many moles of glucose we have. All right. Now, from there, what we want to find out, remember they're asking us how many grams of water we're going to make. So now we can do the same step we did the first time. In other words, we can take our moles of glucose and we can look at the relationship between the moles of glucose and the moles of water. So this many moles of glucose, we want to know the relationship between glucose and water, and we know that for every 1 glucose that goes in, 6 waters come out. And if we solve that, we find that we make 0.05 moles of water. The thing is, they're not asking us how many moles of water we're going to make, they're asking us how many grams of water we're going to make. So we could now take our answer, our 0.05 moles of water, because we know this is how many moles of water are going to be made, and we can convert this to grams because we know that 1 mole of water weighs, and you would go to the periodic table, oxygen is 16, and then you have 2 hydrogens, so a mole of water weighs 18 grams, and when you work this out, you find that you make 0.9 grams of water. And this would actually be your answer to the problem. Now, here's the issue with this. We basically did 3 problems here to solve this. we already knew from our previous slide that we can relate moles of one thing, in this case the glucose, to moles of something else. The problem is they didn't give us moles. So we went back to our mole chapter and we said, well, we can change the grams of glucose to moles, and that was what I did first. Then we can take those moles of glucose and then we can relate moles to moles, moles of glucose to moles of water, and it's a 1:6 ratio. Our answer would be in moles of water, but they asked how many grams of water would be made. So I took my answer and I did a conversion from moles to grams. Now, this is a lot of work and it makes a big mess. So what I'm going to show you now is how to combine all three of these steps, step number 1, 2, and 3, into a single equation. Alright, so this is how we combine it. So we're going to again start with the one piece of information we were given, which is that we are starting with 1.5 grams of glucose. Now, we just said our first step before we can solve this problem is we need to convert to moles because we can only look at the relationship in moles. So to convert glucose to moles, I had said that you go to the periodic table and glucose weighs 180 grams, and so 1 mole of glucose would weigh 180 grams. Our second equation was our ratio, and this is the only step where you go to your original equation and we look at coefficients. Do not look at coefficients when you're doing any other step. So we want to know our relationship between glucose, that's the one we want to get rid of, and the one they're asking for is water. So we have glucose on the bottom, water on the top. We go to our equation, and our relationship is that for every 1 glucose that goes in, 6 waters come out. Alright, if we were to stop here, if I do my canceling here, this converts grams to moles. This is moles of glucose, and our answer would be in moles of water. So our last step was that we needed to convert water to grams. We need to know how many grams of water we're making. So 1 mole of water from our periodic table weighs 18 grams. And now, this is our second convert step. So our 3 steps would be, we're going to convert to moles, we're going to look at the ratio of what we have on the bottom and what we want on the top, and in the end we're going to basically convert our answer to grams of that thing that we were looking for. And when you work this out, you're going to find that you get the same exact answer. So we go like this, 1.5 divided by 180 because it's on the bottom, multiply by 6 because it's on the top, multiply by 18 because that's on the top, and our answer again comes out to 0.9, or significant digits wise, since there's 2 here, I guess it would be 0.90 grams of water. Notice that we did this whole thing this time using one single equation rather than 3 separate equations. 1, step 2, step 3. So let's look at another problem. And you're going to notice that you follow the same steps every single time. This doesn't change. So we are given, that's our first step, 2.3 grams of aluminum. So we're starting at aluminum. Now we need to see what they're asking for. They want to know what mass of aluminum oxide will be made, which is this one. So we're being given aluminum, we're asked for aluminum oxide. Since they gave it to us in grams, our first step is that we have to convert to moles because we can only relate these things to each other using moles. So we would go to the periodic table and find that aluminum weighs 27 grams per mole. That's our first step. Alright, if we stopped here, all we've done is convert to moles. Our second step is to look at the relationship between the thing we have, which is our aluminum, and the thing they're asking for, which is the aluminum oxide. So if we look at this, our relationship is for every 2 aluminums that go in, 1 aluminum oxide comes out. So 2 aluminums to 1 aluminum oxide. If we stop there, our answer will be in moles. So our final step is that we want to convert our answer at this point to grams. So 1 mole of aluminum oxide, and we go to our periodic table, and aluminum weighs 102 grams, or aluminum oxide I mean. And now let's double check that we've set this right. This will convert our grams to moles of aluminum. Next is our relationship, our ratio between our aluminum moles and our aluminum oxide. And then in our last step, we're converting our moles of aluminum oxide to grams of aluminum oxide. And so this time what we'll do is we will start with 2.3, divide by 27, divide by 2, and multiply by 102. And when you do that, working across, you get 4.3 grams of aluminum oxide would be produced. And that's our answer. Okay, so here's one more practice problem. What mass of sodium hydroxide will be produced when 0.25 grams of sodium react with water? So our first step, let's write down the information we started with. So 0.25 grams of sodium. That's what we're starting with. What are we looking for? We're looking for how much sodium hydroxide we're going to make. But our first step, since they gave us grams, is we have to convert, always. So 1 mole of sodium weighs 23 grams. So there's our first step. If we stop there, all we've done is convert from grams of sodium to moles of sodium. Now we're going to look at our relationship, our ratio between the sodium, which is what we already have, and the sodium hydroxide, which is what they're looking for. So in this case, 2 sodiums go in, 2 sodium hydroxides come out. So it's a 2-to-2 ratio, which is the same as 1-to-1. So you don't actually have to multiply by 2 and then turn around and divide by 2. Alright, and our last step is going to be to convert again, because if we were to stop here, our answer would be in moles of sodium hydroxide made, and they're asking us how many grams of sodium hydroxide are going to be made. So 1 mole of sodium hydroxide weighs 40 grams. And now let's double check that we've set this up right. Grams of sodium, we've converted to moles of sodium. Moles of sodium cancels and we get moles of sodium hydroxide. Moles of sodium hydroxide cancels and we'll get grams of sodium hydroxide. We work our way across, 0.25 divided by 23 and then multiplied by 40. And our answer is 0.43 grams of sodium hydroxide. So, okay, so this problem is a little bit different, but you're going to follow the same steps. So it says that we're starting with 125 grams here of sodium nitride. So we write down our first piece of information. And notice that they're asking this time what volume of nitrogen gas will be made. So they're not asking for grams, they're asking for a volume, but we'll get to that in a minute. Our first step is always our convert step, unless they gave it to us in moles, which they didn't. So we need to convert from grams to moles. And okay, so our molar mass here is 65 grams. And that's from our periodic table. Okay, second step is our ratio step. So we were given the sodium nitride, and we are being asked for the volume of nitrogen gas. So we go to our equation, and for every 2 sodium nitrides that go in here, 3 nitrogen molecules come out. So 3. Okay. And now our last step. This is the only step that's different. It's still a conversion step, but they're not asking for how many grams of nitrogen will be made. If they were, we would do what we've done before. We would do 1 mole of nitrogen, and we would look up how much it weighs. But instead, they're asking for the volume of nitrogen. So you should remember from the last chapter that to go from moles of any gas at standard temperature and pressure to volume, 1 mole is 22.4 liters. So since they're asking us for volume, we're going to convert from moles of nitrogen gas to liters of nitrogen gas instead of converting it to mass. And so let's double check. We cancel our grams of sodium nitride. We converted to moles. We looked at our mole to mole ratio with the thing we knew on the bottom and the one we were looking for on the top. And finally, we converted from moles of nitrogen to the units they asked for, which in this case would be liters. So we're going to take 125, divide by 65, multiply by 3, divide by 2, and multiply by 22.4. And our answer comes out to 64.6 liters of nitrogen gas. And that is our answer. All right, so let's do one more of these. So here's our new equation, and this time, let's pay attention. We are being asked how much aluminum, or what mass of aluminum, will make 1.32 liters of hydrogen gas. So our one piece of information we've been given is 1.32 liters of hydrogen gas. This is our hydrogen gas. And they want to know how many grams of aluminum would be needed to make this. All right. So our first step is our conversion step. Now, since they gave us liters, our conversion from liters to moles is that 1 mole of hydrogen gas, or any gas for that matter, is 22.4 liters. Our second step is our ratio. And our ratio is going to be between the one we were given, which is our hydrogen, and the one they're asking for, which is the aluminum. And the relation is, for every 3 hydrogens, we need 2 aluminums. And our last step is our conversion step, and we need to see what they want us to convert to. So 1 mole of aluminum, and they are asking for mass. So that means we're converting from moles to grams, and aluminum on the periodic table weighs 27 grams. Let's check our setup. We went from liters of hydrogen to moles of hydrogen. Then we went from moles of hydrogen to moles of aluminum. And finally, we went from moles of aluminum to grams of aluminum. We're going to start with 1.32, divide by 22.4, multiply by 2, divide by 3, and multiply by 27. And when we do that, we get 1.06 grams of aluminum, and that would be our answer. Okay, our last type of problem, we've learned how to go from simply moles of one thing to moles of something else. That was easy, we just do the ratio. We've learned to go from mass of something to mass of something else. We've learned how to go from volume of something to mass of something else, or vice versa, from mass of something to volume of something else. And our last one is going to be, what if they give you a volume of one thing and they want to know the volume of something else? So take a look at this one. Nitrogen reacts with hydrogen to make ammonia. You start with 15.5 liters of nitrogen. How many liters of ammonia will you make? Now, I'm going to work this the long way first to show you why it's not necessary. So remember what we've learned before. 15.5 liters of nitrogen. Our first step would be to convert to moles. How do we get from liters to moles? 22.4 liters of nitrogen would be 1 mole of nitrogen. Our next step is our ratio. Moles of nitrogen to moles of ammonia, and our relationship is that for every 3 nitrogens there are 2 ammonias, And our last step is to convert to the units they're asking for. So 1 mole of ammonia, and they're asking for liters, is 22.4 liters. So to solve this, you would take 15.5, divide by 22.4, multiply by 2, divide by 3, and then multiply by 22.4. Now, here's the thing. If you're going to divide by 22.4 here, and then you're going to turn around and multiply by 22.4 again, technically these two steps cancel each other out. If you do it the way I just showed you, you'll still get the same exact answer, but it's completely unnecessary. So since the conversion factor is a constant, you actually do not have to do any conversions for a liter to liter problem. You simply go straight to the ratio. So 15.5 liters of nitrogen, the relationship is for every 3 moles, or in this case, really, for every 3 liters of nitrogen, we would make 2 liters of ammonia. And so we take our 15.5, we multiply by 2, and we divide by 3. And we get 10.3 liters of ammonia. All right, so let's summarize everything. So let's use this equation in the upper corner right here for making water. 2 hydrogens react with 1 oxygen to make 2 water molecules. So how would a mole-to-mole problem look for this equation? Well, let's say that you were given 0.5 moles of hydrogen, and you were asked how many moles of water would you make? You would start with your 0.5 moles of hydrogen, and we would simply go straight to our ratio because we know that moles are related to one another. We'd look at our moles of hydrogen compared to moles of water, and we would find, if we go to our equation, that for every 2 moles of hydrogen that go in, 2 moles of water come out, which means those are going to cancel. So therefore, if I started with 0.5 moles of hydrogen, I would make 0.5 moles of water. So for a mole-to-mole problem, you simply use the coefficients and set up a ratio. Here's our second problem type, gram to gram. So let's say you're told you start with 5 grams of hydrogen, and you're asked how many grams of water you would make. All right, our first step is going to be to convert 2 moles, conversion step. So 5 grams of hydrogen, 1 mole of hydrogen weighs, we go to the periodic table, 2 grams. Next, our relationship from the equation, moles of hydrogen on the bottom to what we're looking for, moles of water on the top, and that's a 2-to-2 ratio. Notice that all we've really done is taken this middle step here, and it's our middle step here too. And finally, they're asking for grams of water, so we do a conversion from moles of water. Periodic table would tell us that water weighs 18 grams to grams of water. And then we would work our way across. Grams cancels, moles of hydrogen cancels, moles of water cancels, and our answer ends up in grams of water. Our third type of problem is our gram to liter or liter to gram. So let's say, for example, we are given the same exact problem as before. We start with 5 grams of hydrogen, but we want to know this time how many liters of water vapor would be made at standard temperature and pressure. Well, guess what? Our first step is going to look exactly the same. We're converting to moles. So 1 mole of hydrogen weighs 2 grams. Our second step is also the same. It's our relationship between the hydrogen and the water. And now our last step is the one that's different. Since they're not asking for grams of water, but instead are asking for how many liters of water, we know that a mole of any gas at standard temperature and pressure occupies 22.4 liters. And again, we can double check our math here. Grams of hydrogen got canceled. We converted to moles. Moles of hydrogen was canceled because we converted from moles of hydrogen to moles of water. And now moles of water gets canceled, and we converted to liters of water. And so our answer this time would be in liters of water. Our final type, up in the corner here, was our liter to liter equation. So I'm going to make a little space here. So let's say that you were told that you were starting with 5 liters of hydrogen gas at standard temperature and pressure, and you wanted to know how many liters of water would be made. Since it's a constant, 22.4, you do not have to convert to moles and then back from moles. You go straight to the middle step. 5 liters of hydrogen. Our relationship between liters of hydrogen and liters of water is a 2 to 2 relationship, which would therefore cancel. And so in this case, we would make 5 liters of water vapor. And that is a summary of how to do stoichiometry problems.